Okay, now we define some definitions, and after defining the definitions we will do related theorems. The first definition is in this lecture, it is Boolean ring. We will define what is Boolean ring. Okay, so if you are studying ring, then this definitions has its own importance and has its own face in ring and field. So Boolean ring, it is just like a ring or is called a Boolean ring, or is said to be a Boolean ring, okay, if it satisfies the certain condition. And what is that certain conditions under which a ring or should be Boolean ring? And that certain condition is, we will pick the element from the ring or, and just like we will say that for all x belong to or, we have just like x square is equal to x. This is the condition for all x belong to or, x square is equal to x is the condition. If this condition satisfy on the element of or, then we say that or is a Boolean ring. Okay, the statement of the theorem is related to Boolean ring. So this theorem is actually the application of Boolean ring. The statement is every Boolean ring is commutative. So we know the definition of Boolean ring, and we also know that what does it mean by commutativity. So our target is from Boolean to commutative. So when we will consider Boolean, we will prove that commutativity. Okay, so we take two elements. Here we are picking two elements from ring or, and those elements are x and y. These are the two elements from or, and by the definition of Boolean ring, x plus y square, as we have studied the definition before, x plus y square is equal to x plus y, and x plus y square can be written two times, just like x plus y and x plus y, which is equal to x plus y. Okay, now we multiply x plus y with x plus y. So what is the method? You will multiply x with x, it will be x square, and x with y, it will be xy. And now you will pick the y with x, yx, and y with y, it will be y square, and this is equal to x plus y. Remember that we want to prove the commutativity. Okay, so which means that our answer should be xy is equal to yx. So x square plus x square is equal to x. Remember that. Why? Because it is Boolean ring, so x square is equal to x plus x square plus y, and similarly y square is equal to y due to Boolean ring, x plus y. So okay, now x will be cancelled out with x, and y will be cancelled out with y, and here you will write xy plus yx is equal to 0. Okay, and Now xy is equal to minus yx. Okay, so suppose this is a. Okay, so this equation is a, but we want to prove that xy is equal to yx, not minus yx. So actually we want to remove minus from here. When we will remove the minus from here, it will be xy is equal to yx, which means that our target has obtained. So now we know that x square is equal to x and minus x square is equal to minus x by the definition of Boolean ring. Okay, so it means that x square is equal to minus x, and from these two results, yes, x is equal to minus x. Okay, so if x is equal to minus x, yes, similarly we can prove that y is equal to minus y. So y square is equal to minus y square is equal to minus y square is equal to minus y, which means that in a similar way y square is equal to minus y, and yes, from first this and this you can write y is equal to minus y. So you can put x is equal to minus x or y is equal to minus y in equation A. When you will put in equation A, you will get the required result. Xy is equal to minus time y is equal to minus y. Yes, y is equal to minus y, and x, and this minus minus will be plus, so you will get the xy is equal to yx. Okay, so minus y and this is x, so xy is equal to yx. Hence we have proved the commutativity. Okay, so every Boolean ring is commutative. So after proving this theorem, this was a very simple theorem. Now we will move a little bit next, and we'll do some exercise and some examples, some theorem. Also there are a lot of definitions that we will do in ring and field. Okay, so here I am defining a definition. The definition is nilpotent ring. So now we define what is nilpotent ring. It is very simple. It is just like, let a ring for which an is equal to 0 for all a belong to R, for all a belong to R is called, this is called nilpotent ring. This is called nilpotent ring. This is the definition of simple, very simple definition. An is equal to 0. If this condition is satisfied for all a belong to or, then this is called nilpotent ring. Now there is a theorem related to this definition. This theorem is a very simple theorem, not a big or a little conceptual theorem. It is just in 2 or 3 lines. We will do it. And first of all, the statement of this theorem. A nilpotent ring is has ring has zero divisor. Okay, given that nilpotent ring, and we will prove that it has zero divisor. Okay, let me complete the proof of this theorem just in 2 or 3 steps. Okay, let R be a, of course, given that nilpotent ring, let A is not equal to 0 is an element of R. Okay, and R is nilpotent ring, then this means that by the definition of nilpotent, an should be equal to 0, and an can be written as just like it is a and a raised to the power n minus 1 is equal to 0. So what does it mean by a raised to the power n minus 1? It means that it has zero divisor. So this is the definition of zero divisor. A dot mean multiply. Yes, it is the definition of zero divisor, which complete the proof of our theorem that a nilpotent ring has zero divisor. Okay, so a nilpotent ring which is R, it has zero divisor. So this was the very simple proof of this theorem, and now we will discuss some other examples. Okay, there are very simple examples over here. The first example is just like it is find the zero divisor. Find the zero divisors of Z6. So when we talk about Z6, then first of all our mind click on the element of Z6. So what are the elements in Z6? The elements in Z6 are 0, 1, 2, 3, 4, 5. Okay, so actually we are going to construct the table over here, but I will be sorry a little because the line may be a little bit not okay. So 0, 1, 2, 3, 4, 5, and the similar lines, yes, 0, okay, under multiplication 0, 1, 2 and 3. You will write the element horizontally and vertically. So after writing the element horizontally and vertically, it will be just like as 0 multiplied by 0. First of all, construct the lines. Okay, Yes. Maybe a little bit straighter. Yes, vertical lines are a little bit difficult to draw on the tablet because I am using this tablet just from last 3 or 4 days, and I am not a little bit quite well for writing on the tablet. So okay, multiply 0 multiply by 0 and 0 multiply by 1. So all these elements, when or multiply by 0, all the elements should be 0. And now you will pick 1 with 0, 1 1 2 3 4, and it is 5. 2 2 and this is 4. Yes, and 2 3s are now 6. 6 means 0. So here you will write not 6, you will write 0 because remainder is 0 after divided by 6. So 2 4s are 8 and the remainder is 2. Similarly 2 5s are 10 and remainder is 4 after divided by 6. Now 3 0, 3 1s are 3, 3 2s are 6, which means 0, and 3 3s are 9 and the remainder is 3, and 3 4s are 12, remainder is 0. So these are the elements. Remember that when we talk about z6, after multiplying we always write the remainder. Okay, so here we are writing the remainder after dividing by 6. Now 5 zeros are 0, 5 1s are 5, 5 2s are 10. After dividing by 6, the remainder will be 4. 5 3s are 15, and after divided by 6, our remainder is 3. Similarly 5 4s are 20, and after divided by 6, the remainder is 2. Okay, so this completes the table. So here from this table, since we know that 2 multiplied by 3 is 0, also 4 multiplied by 3, 2 and 3 is 0, 4 and 3 and 4 is 0. So this means that 2 3 and 3 4 are 0 divisors. Okay, 2 3 0 because remainder is 0, 3 4s are 12, after divided by 6 we get the remainder 0. Okay, so this means that 2 3 and 3 4 are, these are non-zero. Okay, so there are two types of just like 0 divisor. 2 3 are 0 divisors, okay, and similarly 3 and 4 both are 0 divisors. So this complete the example. Now we will take another example, and this example is similar example, a little bit of difference. So we check that what we want to find in this example. First of all, it is we want to check Z5. Okay, the previous example was related to Z6 and this example is Z5, and we want to check that Z5 for integral domain. Okay, so integral domain or field Z5. Z5, first of all we will list the element in Z5. The elements in Z5 are 0, 1, 2, 3 and 4. These are the 5 elements in Z5. Set of residue classes module 5. It is also called set of residue classes, and the element for the set of residue classes are 0, 1, 2, 3. Similarly, we will construct the table and write the element horizontally and vertically 0, 1, 2, 3, 4. Yes, now we will write the element vertically. So all is better, but when I draw the table, the lines are a little bit okay. 0, 1, 2, 3. Okay, remember that you just want to clear the concept related to ring and field. So I am trying to my best to give you good writing, but sometime just like over here I have a little bit difficulty for drawing the table. Okay, it is because using the tablet, and maybe there is a technique to use this tablet, but I didn't find any technique. Just drawing. Yes, the horizontal lines are good to draw, but the vertical lines are a little bit, yes, these are not straight. Okay, so under addition, 0 plus 0, it will be 0, 0 plus 1 and 2, 3, this is 4. Similarly, 1 plus 0, it will be 3 and 4, just like 0, 3. Yes, it is very simple. So where you will get 5, you will get 0. Where you will get, just like if your answer is 7, 7 means your remainder is 2, and if you get 8, then that means that your remainder is 3. So you will write the remainder after adding. Okay, if your answer exceed above 5. Okay, so you have now constructed this table, okay, of Z5, and we want to check it for integral domain. You want to check it for integral domain or field. So it means that all the properties of integral domain should be satisfied, or if you are talking about field, the first is 0 is, if we check over here, 0 is the identity element. Okay, yes, because after adding 0 we get the same element. When we get the same element, and this defines the identity in any set of residue classes. So here 1 is the inverse, because 1 plus 4 is 0, so additive inverse should be 0. So when we the inverse of 1 is 4, and in this table associative law is also obvious, and a plus b is equal to b plus a, of course, is also obvious. So this means that is an abelian group Z5. Under addition, we have proved over here that Z5 is an abelian group under addition. Okay, because the property of group of an abelian group has satisfied. Okay, so what is our next target? We have proved that Z5 is an abelian group. Now what you want to prove? If Z5 is an abelian group, so our target is integral domain or field. So it means that when we talk about a field, then it means that we will also discuss about under addition it should be abelian group, and under multiplication, okay, under multiplication it should be semi group. Okay, by the definition of it should be again abelian group, sorry, for ring it should be semi group, and for field it should be an abelian group under multiplication. Okay, so now we again draw this table under multiplication. Okay, now you will write the element just like horizontally and vertically. Okay, so yes, 0 0 0, and just like 1 1 plus 1 2, no, 1 multiplied by 0, yes, it's okay, and here it will be 0 and 1. So okay, correct it first. It is 0 and it is 1. Okay, 2 3 4, 0 2 4, and the 6 means 1 and 3. It's okay. So 0, this is 3, and 6, yes, 4 12, that is 2. Now 4 zeros are 0, this is 4 and 3, yes. So this completes the table under multiplication, and in this table if we look, then of course A and B are in Z5, yes, it is low. A and B belong to 5. This means that A dot B is equal to B, means abelian. Yes, under multiplication we want to check its commutativity. Okay, and also we check that A dot B is equal to 0. Yes. So what does it mean by dot B is equal to 0? This means that A is equal to 0 belong to, yes, Z5, belong to Z5. Okay, so this means that it has zero divisor, and of course it is an integral domain. Zero divisor means, okay, when we talk about the zero divisor, then this means that yes, there does not exist, yes, hence Z5 has no zero divisors. Okay, hence Z5, if it has no zero divisor, then it means that it is an integral domain.